Okay, so I'm picking back up at number 38. What massive NaCl did you add to 1 liter of water in an ice cream maker to make a solution that freezes at negative 10 degrees Celsius? Assume a complete dissociation of the NaCl and a density of 1 gram per milliliter for water. So my equation I'm using here is delta TF equals IKM. And the I is going to be, or this K is 1.86. This should also be given to you. This is molality. And this I is going to be basically a dissociation constant. It's basically how many number of particles that the compound dissociates into when it's put into water. So NaCl, for example, is going to dissociate into Na and Cl, which is 2 particles, so it's going to have an I of 2. If I had something like MgCl2, when it dissolves into Mg2 positive plus Cl and another Cl, so that's going to have a constant of 3. So just these values are often experimentally determined, but for the most part they follow these patterns. It might deviate by like 0.1 or something like that. So to do this problem, it gives me my delta, my change in temperature already, which is just going to be 10 degrees. So my I for NaCl, which we described as 2, my K is 1.86, and that's just specific for water. And it asks about my molality, which is going to be moles per kilogram of solvent. So it tells me that I have 1 liter of solvent. That's akin to, so 1.0 liter equals 1,000 milliliters, which equals 1,000 grams, which equals 1 kilogram. So that's kind of easy. So when you multiply this side together, the right side, you're going to get 10 equals 3.72 times basically mole per kilogram. So when I divide 10 by 3.72, I get 2.86 equals this like X amount of moles per kilogram. So multiply it over, I get 2.86 moles of NaCl. And now it wants me to find the mass. So I'm going to convert 2.86 times, so that's right there. So the mass of NaCl is 58.353. And when you do that, you should get 157.1 grams per NaCl. So that would give us A. So 39, which of the following is true? The Van Hoff factor, well, this I is the Van Hoff factor. So this Van Hoff factor for glucose is 24. No, that's false, because glucose doesn't separate, it doesn't ionize in water, it just stays as is. Like if I went into it, it's not going to separate, it's just going to remain as glucose. It's not going to ionize. These are all covalently bound, so I wouldn't expect it to dissolve. I mean, you can have covalently bound, like, because you have HCl, but these aren't, it won't ionize. So just think of what's soluble in water. There's the solubility tables, but for most parts it's going to be something like NaCl or some sort of ionic compound. So this is actually going to be a Van Hoff factor of 1 because it dissolves into 1 particle. The partial pressure of a solute is less than the pressure of the pure solute. Well, this wording is kind of off. I would think solvent versus solute. So the partial pressure of a solvent is less than the pressure of the pure solvent. So, like maybe solution, I don't know. This wording is off, but I know this is going to be true because when I add, when I create a solution, I add this solute to it, I add an extra, I'm adding something that can exert an extra force. So this solvent now exerts a force on the solute, so that's an additional force that's going to hold it back from vaporizing. So in doing so, I'm decreasing my partial pressure. So that is true. But let's just check the other ones. The solubility of a solid decreases with increasing pressure, and I know that's false. When I increase the pressure, I'm forcing these particles down and I'm forcing them to interact, so I know that's false. And then D, adding a solute to water will increase the freezing point. No, it's going to decrease the freezing point. It'll elevate the boiling point. So that's false. So the answer there is B, and we just confirmed it. And for the last one, rank the intermolecular forces by increasing strength. So dispersion's weakest because everything has it. It's going to be less than dipole. And think of hydrogen bonding just as extreme dipole bonding. So it's got to be less than, well, dipole has to be less than hydrogen. And then my next is ion dipole. So that's pretty much it. I'm sorry that it was a little messy in the Opal session, but really thank you to everyone who came out. Reminder, I will be going over these eventually, just not now because you don't need it for tomorrow's exam. Hope you all do well. Reach out to me if you have any other questions. You can come to my session on Wednesday if you want to talk about, or like if you can remember any of the questions. But anyways, that's it. Thank you guys.